seeing that.
Yep.
Okay, great. Well, I hope the course is going well for everyone. So yeah, I think single trial analyses is one of, if not the most valuable capability enabled by NeuroPixels, and hopefully by the end of this short talk, I'll convince you that that's true. So let's get started. I want to zoom sort of way out and sort of ask, what are we doing here? And like, what is the goal? And so you guys are learning about doing analyses of your neural data. These analyses will yield some statistical description of the data, of course. And really, what we're trying to do is go from a statistical description of the data into some insight about how the brain works. And maybe it's obvious, but like this is really hard. This is our job as scientists is to make this step. And the reason this step is hard is because it's often or pretty much always requires some sort of logical steps or assumptions. And we'll talk about that a little bit here, and I'll talk about why single trials makes us maybe a little bit easier. And it's important to know that as our analyses get more and more complicated and our statistical descriptions get more and more complicated, I think this final step becomes even more complicated as well. Okay, so I want you to imagine that it's sort of 20 years ago and you're recording from a neuron with a single electrode. So you have one neuron at a time. Say you show that neuron a visual stimulus, and on a single trial, what you get is just a bunch of spikes and some gaps in those spikes, right? And pretty much what we're always going to do in this case is we're going to take some sort of window or kernel, in this case a 50 millisecond sort of boxcar window, and convolve that with the spikes. And we're going to get some estimate of this neuron's firing rate on a single trial. And what you should notice is that this kind of looks like garbage, right? Like, it's very, very noisy. This is a problem, right? It's kind of hard to infer much from this very noisy firing rate plot. And so what we do as scientists is we repeat this many, many times. We show the same stimulus, and we get many trials, right? So now I'm showing you the single trial firing rate from a single neuron over many repeated trials. So this looks even crazier. And so what we do is we average the activity across these repeated trials. And maybe we get something like this. Maybe we have two conditions where we have a preferred stimulus and a non-preferred stimulus. And I want to sort of talk about two really common, often implicit assumptions about how we interpret trial average data. All right. So the first one is what I'm going to call the ergodic assumption. Okay, so let's look at this PSTH, which is from a single neuron, right, averaged over many trials. And when we look at this PSTH, like how are we going to generally interpret this? We interpret this, oh, okay, this neuron has a transient increase in firing rate when the stimulus comes on, and then it slowly decreases over time, for example. And it's a little bit higher when it's the preferred stimulus versus the non-preferred stimulus. But of course, this is only true on average. I just showed you the single trials, which is just spikes and gaps. And so, in other words, there's sort of this implicit assumption often that the average of one neuron across many trials is representative of something that the brain is doing on a single trial, right? Like this PSTH is not a feature of the brain, it's a feature of the statistician. And so we need to have one additional assumption to make this meaningful for what kind of information the brain has access to. Okay? And what that means is that firing rates really only make sense in light of neural populations, right? A single neuron really cannot have a firing rate on a single trial. It's just spikes and gaps. And if you want to dive more into this idea, which I really think is important to how we think about analyzing neural data, I highly recommend these two papers. One is a classic from Shadle and Newsom, and one is much more recent, which I think is a really important one. Okay, there's one more assumption I want to talk about, and this is what I'm going to call the homogeneity assumption. And here, let's imagine, right, you have a population of activity. Let's say you take the average, you have some way of combining that activity to sort of a 1D variable over time. You average that over trials, right? So maybe it's the firing rate, maybe it's the PC1, some other kind of dimensionality reduction technique, right? And you see that, okay, population activity ramps up for the trial average activity. And another very common implicit assumption here is that this trial average activity is representative of what's happening on single trials. So the single trials maybe look, you assume they look like this, like there's some noise around it, but generally we assume that the single trial is also ramping up monotonically. Uh, and this is an assumption, right? We assume that the trial average activity is representative of single trial activity. Uh, and what I'm going to show you today is this assumption just does not hold in decision making, really any cognitive process where the behavior is completely internally generated. And more generally, averaging activity across trials is a hack necessitated by imperfect data. And as our data gets better and better, we should really make sure we're relying on it less and less. Okay, so let's dive into a concrete example. I'm going to talk about some work I did in my PhD, where we have monkeys performing a classic random dot motion discrimination task. In this task, a monkey fixates at the screen. A bunch of randomly moving dots come on, and then whenever the monkey's ready, the monkey judges the net direction of the motion of these moving dots and reports its decision with an eye movement to the corresponding choice target. And critically, in this type of task, really any decision-making task, there's no such thing as a repeated trial. Every single choice is determined by a unique trajectory, right? You can make the same decision, even take the same amount of time to do it, but the way you got there can be completely different from trial to trial. So averaging is across these trials is a little weird. It's going to hide some important things. So let's formalize this a little bit more. In these types of evidence accumulation tests, we know that decisions are well described by what's called a bounded evidence accumulation model, or very similar to the drift diffusion model. And in this task, we're going to assume that the sensory motion input is transduced into momentary evidence on each sample. And what the brain is doing is integrating from that momentary evidence distribution in every trial. And it sort of has a competition between a rightward choice and a leftward choice. And the accumulator that reaches its sort of decision threshold first is the choice you're going to make. The amount of time it took to reach that threshold is your reaction time. And so here's an example of one single trial where you ended up making a rightward choice. And critically, if I were to run this over again, right, you get different noise. And so you would have a completely different trajectory, which might yield the same choice, might not, might yield the same reaction time, might not. But they could be from the same stimulus condition. Okay, so the sort of classic work in this task has been done in an area called the lateral interparietal area. The main thing you need to know about this area is that neurons have spatial response fields. So they have parts of the visual scene that they care most about. And when you place a choice target within one of these response fields, average activity, so here I'm showing you the average across many neurons, across many trials, looks what you'd expect from these bounded evidence accumulation models on average, right? So here, when the motion is strong, you have strong ramping up or down. When the motion is a little weaker, the ramping is less strong. And when you have a condition where there's just no motion at all in the stimulus, you have something that looks flat, again, on average. But critically, yeah, and then in between for those. But critically, these single neuron averages over many decisions, like this is not what we think is happening on a single trial. So if we zoom in on a noise trial, right, that looks flat on average, what we hypothesize to be the case is that you have drift diffusion paths that underlie this average activity, right? So the average might be a ramp or the average might be flat, but the single trial dynamics are completely different on every trial. All right. Now, when we record from one neuron at a time, we have to average. We don't have access to these single trials. But now we have neuropixels. We can record from many neurons at the same time. We can finally get access to what these dynamics look like. One other thing is that when you align the activity to the time of the saccade, to the time of the eye movement, activity seems to coalesce to a stereotypical firing rate as if some threshold is being applied to that. So again, consistent with this idea that there's a decision threshold being applied to this activity. All right, so I'm going to show you one example session that I collected using our pixels probe. probe. So on the left is trial average activity from a population of neurons from that single session. So I'm just showing you that we can replicate what we found in the past. But now that we have a population that's recorded simultaneously, we can test this idea that the average activity is comprised of drift diffusion paths. So now what I can do is I can look at many neurons, right? The single neuron firing rate, but for many neurons from one trial. And maybe it looks something like this. So again, this looks like noise. So then we can say average or do some other kind of dimensionality reduction to reduce the dimensionality. And maybe if we average, we get something that looks like this. So now this is the average across many neurons on a single trial. All right, so this is just a simulation. So now I'll show you some real data. So again, here's one trial, which is the average of a population of LIP neurons on a single trial. We can look at many trials, and just visually, we find that it looks a lot like what we'd expect from drift diffusion. Also, we can look at activity aligned to the saccade. We can focus on just the pure noise condition. And now when we look at the single trials again, we find within this condition, the single trial activity reaches a point of minimum variance right before the saccade. That's sort of this darker region here, right? So consistent with the trial average activity, but something that didn't have to be the case. All right, and then finally, I can show you a different motion strength, right? So we see that the single trials look like diffusion paths, and the pure noise, the mean might be more flat. When the motion is stronger on the right, the mean, has some upward drift to it, but there's always diffusion. And we can now do analyses directly on the single trial activity. So for example, a first pass prediction of a drift diffusion process is that the variance should increase across trials as a function of time, and that's exactly what we see. We can also do slightly more complicated analyses where we look at the correlation matrix across single trials, and we can have a prediction for what we'd expect from a diffusion process, and we find that the data matches that closely. Don't worry too much about the details here. The point is just that we can do analyses directly on the single trials, right? We don't have to average across trials and then make all these assumptions about what these trial averaged activity is comprised of. Of course, there are other assumptions that come into play, but we can get rid of some of them at least. Okay, finally, I want to make what I think is a really important point, which is that trial averages may obfuscate differences that exist across areas. So here's the trial averaged activity and the single trial activity in LIP. In this experiment, we also recorded from neurons in the superior colliculus. And when we look at the trial averages in the superior colliculus, we actually find that they look qualitatively similar, right? Activity ramps up and down depending on motion strength. Maybe the main difference we see is this large saccadic burst, which we've known about in the literature for years. But I think qualitatively, you'd look at these two PSTHs of these two populations, and you see they're probably doing something really similar. Distributed computation, everything is everywhere and whatnot. But really interestingly, when we look at single trials, we do the same exact analysis in colliculus, we see something that looks completely different. We see the saccadic bursts on the single trials as well, but what we see here and what's not apparent in the trial average activity are these what I'm going to call non-saccadic bursts, right? So we have these sort of bursts of activity that look like the saccadic burst, but they are occurring throughout the decision. And because they're not aligned to any specific trial event, when we average across trials, they just get completely averaged over. You'd never know they exist if you only look at trial average. And critically, what this means is that you can have similar trial average activity in two areas, but completely distinct single trial dynamics, and you'd make completely different conclusions if you looked at trial average versus single trial activity. All right, so some preaching there. All right, so I'll summarize. I showed you, or hopefully convinced you, that averaging over trials is a hack that may obfuscate important insights. There's no such thing as a repeated trial in decision making or cognition more generally. Each decision arises from a unique trajectory. The idea of a repeated trial is kind of strange. If we want to understand how neural activity gives rise to decisions, then focusing on single trial dynamics will be critical. We really have to understand brain areas at the level of single trial dynamics, not trial average activity. And finally, now we have neuropixels, and it gives us access to these single trial dynamics, and we should take advantage of that. So I'll end there, and I'm happy to take questions.